So we're going to keep on going and keep looking at refraction of light waves. This is the two-dimensional stuff we started last time. So, of course, the big reason why light refracts and changes direction when it changes mediums is because it goes faster or slower depending on the materials you're actually using. So we're going to look at that first. So, for example, we have some waves coming in, maybe moving towards the right, something like this, and then it hits a barrier of some kind and goes into a different material, and all of a sudden maybe it looks something like this. Okay, so right here, when it changed mediums, it changed whatever material is going through. As you can see, the actual speed went down and the wavelength went down. So the speed gets smaller, so since the speed gets smaller, the waves sort of catch up with each other, again, like a traffic jam type idea, and so the distance between them actually goes down. So if the speed goes down, the wavelength gets smaller as well. But if you remember from your expression v is equal to frequency times lambda, the wave equation, your v got smaller and your lambda got smaller, but the frequency stays the same. You actually have a constant frequency. That is the one thing that will not change. The frequency is actually dictated by the actual wave source, and it doesn't change. That's why if you're wearing, a red swimsuit and you jump into water, it still looks red underneath the water because the frequency doesn't change, and frequency is what actually dictates the color. So the wavelength can change, the speed can change, but the frequency will always stay the same. Okay, so it's all about changing the speed. That's the key right there, is the speed changes, and because of that, the wavelength then changes. So because of this, there is a measurement that kicks in. It's called the index, and the index of material basically tells you basically how much the speed changes. Okay, and it's often referred to as the index of refraction because it's typically associated with refraction. Now, it's actually a really simple idea. If it's going here, right here, this is where it's going faster. This is where it's going slower, I can tell because the waves are all squished together. If it is going to go 2 times slower, well, then the index is equal to 2. It's just that easy. Okay, so if something has an index of 3, it's going 3 times slower. That's basically how it works. It's really simple. And it is always compared to the speed of light in a vacuum. So it's always compared to speed of light, the 3 times 10 to the 8. Okay, so for example, if here it is traveling at 3 times 10 to the 8, and over here it is traveling at 1 times 10 to the 8, well, it's going 3 times slower, the index for this material would be 3. It's just that easy. Okay, so it's just a ratio between the two. So to find the index for a material, and the symbol for index is a lowercase n, all you do is you try and just take the speed of light in a vacuum and you divide it by the speed of light in the material, whatever it happens to be, and that tells you the index. Okay, so if this got 3 times slower, this would be, the v would be 3 times less, and c divided by this would give you a value of 3. Okay, so the index of material is c divided by the speed or whatever it is, and you often see the speed index x or vx because x just represents whatever material you're talking about. So because the speed of light is at the top and you can't go faster than the speed of light, the index value is always going to be bigger than or equal to 1. Of course, you get 1 if you just talk about speed of light in a vacuum, but the index is always bigger than 1 because the speed down here is not going to be bigger than the speed of light in a vacuum. It always gets slower. It goes into water or glass or whatever you want, it's going to slow down. Okay, so that's how you can calculate the speed of light in different materials as well, by reversing this. For example, if you take just average glass, the index for glass is about 1.5. There's different types of glass, but on average it's about 1.5. So if you wanted to find the speed of light in glass, all you have to do is take the c, speed of light in a vacuum, and divide by the 1.5, and you can find that light travels at about 2 times 10 to the 8 meters per second in glass. So that's how fast light goes in glass. Okay, so that's the basic idea behind the index. And we haven't incorporated any refraction yet, but this is the idea behind the index because it's that difference in speed which causes light to change direction in the first place. So now let's see if we can use this, and we're going to apply this idea to actual refraction and changing direction. So if we go back to the simulation that we used last time for a second, we have this guy right here, and we can have the wave rays. There's the wave rays, there's the waves themselves, and we looked at how if you increase, what I'm actually doing is I'm increasing the index of refraction for the material at the bottom, and that causes the waves to slow down, which causes them to get smaller. Remember, the frequency is the same, that's why they're red on the top and the bottom. And if I then angle it, we get that refraction thing that we're talking about, and that's this diagram on the left is all about. And of course, we can use the wave ray as well, which makes things a little bit nicer and cleaner, but this is what we're talking about in terms of the actual situation. Okay, so we're going to look at the situation, look a little bit at the geometry of the situation, and sort of see how the refraction idea sort of works and how we get some certain quantities connected to it. So we're going to start just by labeling a couple things here. We'll just take a nice simple situation, something really common, like suppose this is air and this is water. It doesn't have to be, but this is a lot of people think of like going from air to water for light to refraction. It's what most people think of, so why not just use it? So for this right here, we've got a few things that we can actually label and measure, and this is the same page that is was posted on your class website, so you can actually go along with it and sort of fill things in. So we'll be doing a few different things in derivations with this. So first things first, I'm going to label a couple things. Up here, I've got my wave fronts here, and of course the distance from here to here, that is the wavelength in my first, I'm just going to wavelength one, wavelength in my first material. And you can see in the second material that that wavelength has gotten smaller because light travels slower in water. Okay, and we can see it's changing direction. Of course, if we're talking about direction, angles are important. So here you can right there, I've got an angle in the air over there, and I've got an angle in the water over there, and you can see the angle is smaller in the water. Now, typically we measure angles from the normal for this type of thing that we sort of mentioned before with the reflection, but we won't worry about that right now. Now, there has to be something that connects the stuff in the top and the stuff that's at the bottom. Okay, it's a lot of geometry involved with this type of stuff. There's geometrical type stuff, and there has to be something that they actually have in common. There's a common measurement that they have. Well, it's not the wavelengths, it's not the angles, but if we look at the actual boundary itself, where they actually come together, they share that black line distance right there. The distance between the contact points here for the air is the same as the distance for the contact points for what's happening in the water. So we can use that common measurement and try and tie things together. So how are we going to tie these things together? Well, if I just take this little wavelength measurement right here and I move it down here like this, okay, and I do the same thing for this one, maybe you can see what actually happens here. We actually end up creating a couple triangles. We actually get a couple triangles right here, this right here, right there. That is the wavelength right there, and that is the wavelength right there. These are perpendicular, and we actually end up creating two right triangles. And those two right triangles have the common measurement d, which is the hypotenuse. So we actually have two triangles with a common side, so I can use that common side to sort of tie things together. Okay, and if I carefully look at the sides, there's my angle right here. The opposite is the wavelength, and this d is the hypotenuse. And opposite of the hypotenuse, that would be sine theta. So if I did sine of the first angle, that'd be opposite of hypotenuse. That would be the lambda 1 divided by d. And if I did the same thing for the other one, that'd be lambda 2 over d. Well, these two triangles share that d value. So if I solve both of those for D, and I can equate them. I can put them together, and I will have sine theta 1 over lambda 1 is going to be equal to sine theta 2 over lambda 2. Just by solving this for D, solve that for D, and then just equate them. And now I've connected the angles for both sides together, which is important for Snell's law, which is what we're going to derive, which is the rule for refraction is all about direction changing. Okay. So I'm going to do is I'm going to rearrange this a little bit, do a little cross multiplying and get some things together and get a ratio going. If I do this, I can do sine theta 1 over sine theta 2 is equal to lambda 1 over lambda 2. I'm just going to take these two guys, cross multiply, and sort of switch those two around, basic algebra. And I'm going to use this as a starting point for something. Okay, so I'm going to take that right there. I'm going to take this, and I'm going to use it over here. Okay. Give myself a little more room here. Okay, so this is my starting point. Now, what I'm going to do is I'm going to use your basic wave equation. And of course, the wave equation is the speed one. So lambda, lambda is, of course, speed divided by frequency. There we go. Speed. I'm going to use that for both of these. So I'm going to replace this with speed 1 over frequency 1 is divided by speed 2 over frequency 2, just like that. Okay. Now the thing is, if you remember, the one thing that doesn't change are the frequencies. So these frequencies actually cancel out, and I am left with V1 over V2. Okay, now this should look familiar from the index stuff that we just did. Now if you remember, V for a material is C over NX. So what I can do is I can actually take that and put that in here as well. Seems kind of silly, but that's what we're going to do. So this would be C divided by N1 over C divided by N2. And what ends up happening, the C's cancel out, gone, gone. And I've got an inverse fraction. I've got a fraction divided by a fraction. Of course, when you divide two fractions, you flip the second fraction and multiply it. So I'll end up with N2 divided by N1. And there's my indexes that we looked at before. And that's really important because indexes are a great thing to know about a material, because if you know the index, you know how you figure out how fast it's going to go, how much the wavelength changes. There's lots of things you can actually find. Okay, so let's put these things together. That is what I started with, and this is equal to this. So what I've got is sine theta 1 is equal over sine theta 2 is equal to N2 over N1. Now I'm going to cross multiply them. If I cross multiply them, I end up with N1 sine theta 1 is equal to N2 sine theta 2. Now this is called Snell's law, and it's named after a guy named Snell, obviously. And this is the rule and calculation used to calculate the direction change for materials when they refract, when they change materials, and that type of stuff. It's based on the angles, obviously, because angles are really important for direction, but also the index, because the index is one of the most common things known about a material in terms of how light will go through it. And the index is a really, really important part. It's one of the most important values for stuff like this, because if you know the index, you can solve for pretty much anything. Okay? But that's what you get out of it. That's called Snell's law. So we'll be doing some practice of this and using the indexes to try and find different values. Okay, and even if I went back to my simulation right here, okay, I've got my different angles and stuff that I've got an angle here. There's my first angle. There's my second angle. I could use the sine thetas of those angles as well as the indexes to solve for anything that I want in the situation. Okay, and there's even a little protractor here that we can crack out. And you can see the zeros are right along this normal dotted line, and the angles are measured from that normal. They're measured from not the surface, but the normal to the surface. Okay, and you can see you've got a bigger angle here. This looks like around 50-ish degrees or so, and this one's only around 20 degrees or so. Okay, and the higher the index, the smaller the angle is going to be. Okay, so we will be practicing with this a little bit and sort of see how this works.